Okay, so we're going to start off with intermolecular forces. Then we're going to talk about the properties of liquids. We're going to go to the transitional phases, phase diagrams, solid materials, and this kind of gives you the whole idea of what we're going to be talking about in general. Okay, so we talked about gases. You guys remember gases? Okay, were you feeling pretty confident with gases? Give or take? Yeah. PV equals nRT, wasn't too hard, right? Wasn't too hard, right? Okay. So when we're talking about gases and everything, when gases are dilute, they're going to be they're going to behave kind of similarly, right? There're not going to be too many differences between them. Okay. Now, when chemical substances, when we're talking about the solids and the liquids themselves, it's going to be dependent on what we're talking about. Okay. And that's going to be kind of important for us, okay, so that we can kind of understand. And part of that is going to be due to what we call intermolecular forces. So when in doubt, you want to say intermolecular forces. You guys got that? When in doubt. Okay. Yes. It would be nice if it is styrofoam cups, but any cup would work. I think that we're going to have them do this individually. Yeah, and there should be dye. There should be little bits of dye. It should be in the chemical cabinet that says common chemicals on it. Yeah, so it's on the back wall on this side. 5 styrofoam cups. What works out? 1, 2, 3, 4. Works out perfectly. If somebody else comes, then we'll deal with it later. Yeah. There's 8 of you guys on the roster. So. Okay, so intermolecular forces. Intermolecular forces are going to be the forces between, okay, so intermolecular forces and intramolecular forces. Intermolecular forces are the forces between 2 different molecules, okay? So like for instance, water. So we have one water molecule and another water molecule. They're going to be interacting in this way. And we'll be talking about those forces. Okay. Intramolecular forces. Those are the forces that are going to be within that single molecule. Okay. So intra. Okay. Intermolecular forces are kind of like the bar, you know. Okay. Intermolecular forces between 2 molecules. Okay, so you guys can kind of see that here. Okay, now bonds and stuff we know are strong. Okay, our intermolecular forces are going to be weak, but they're going to be somewhat cumulative, right? So if you have a long chain, let's say DNA, it's going to be strong because of the interactions. Each of those intermolecular forces, intermolecular forces that are going to be active. You know? Okay, so you guys recall we talked about kinetic energy and when we heat things up, right? So when we heat up a solid, it becomes a liquid, then becomes a gas. Okay, and we know that that is a result of kinetic energy, right? Things are moving, right? Okay, and so the more we heat things up, okay, the more energy that we're putting in that system, the more kinetic energy that's going to go on, right? Okay, so as we look at this, as we increase our kinetic energy, or as we increase the temperature, the kinetic energy is going to go up. Okay, it's going to move faster, right? So as you go from solid to liquid to gas, the molecules are moving faster. Now, intermolecular forces, it's going to actually be just the opposite. They're going to increase as we go the other way. As we go from a solid, then we cool down to a liquid, then we cool down to a gas. Now, this kind of makes sense if you sit there and you think about it. Think about the water molecule. When it's a solid, all of the water molecules are interacting together. They're tightly interacting. And then as we heat things up right? Those forces between those two water molecules are they're being separated, okay? And the more we heat it up, the more it's being separated, right? Okay. So the strength of intermolecular forces, the IMF just stands for intermolecular forces, they're going to vary, okay? The strength of each one is going to vary a little bit, okay? So if you take a look at our table down here, you guys can see, okay, so if we have an ion dipole, you guys remember what an ion is, something that's positively charged or negatively charged, interacting with something that is dipole, meaning that you have a neutral charge overall, but something is being pulled one way or the other, okay? Okay, so like for instance, when we talk about water, we know that oxygen gets the electron majority of the time, and hydrogen only gets it a little bit of the time, right? So it forms a dipole, right? So that the oxygen has the electron on its side most of the time, and the hydrogen doesn't. So we have a negative charge on the oxygen or a negative partial charge on the oxygen, and then a positive partial charge on the hydrogen. Okay, so let me. Okay, so this here represents a dipole. Okay, now if we have a negative ion, let's say we have chlorine. Chlorine has a total negative charge. Now, if I put it next to oxygen, what's going to happen? Kind of push away, right? But we know that if it's next to hydrogen, hydrogen is going to be attracted to it, right? So that the water molecule is going to orient itself so that it's interacting with the chlorine, right? Now, the energy associated with that connection there, ranges from anywhere from 40 to 600 kilojoules per mole. Okay, so, and that's the case of when we have an ion and a dipole. Now, when we have something like water interacting with water, and it forms what we call a hydrogen bond. A hydrogen bond is just an interaction between, an intermolecular interaction between hydrogen between something that is, you guys remember your electronegativity, right? Something that has a strong electronegativity and hydrogen. So something like fluorine or chlorine or oxygen. Yep. Okay. So in this case, if we had water interacting with water, this guy forms what we call a hydrogen bond. And we draw it like this. And it's not a real bond, it's just an interaction. It's kind of like a fist bump, right? So it's just kind of like fist bump. They're not connected really, but they're just interacting because we have something that's partially positive and something that's partially negative. And they just kind of loosely attract to each other. Okay. Now that interaction there is about 10 to 40 kilojoules per mole in energy. So when we have dipole-dipole, now dipole-dipole basically means that you're forming two dipoles, kind of like what water does, but you don't have that hydrogen because that hydrogen and oxygen, that strong change, that hydrogen bond is a little bit stronger than that dipole-dipole. So if we have something like sulfur and chlorine, right? So those guys, dipole-dipole, it's about 5 to 25 kilojoules per mole, okay? So weaker than that hydrogen bond. So when we think about strength of bonds, or these, not bonds, these intermolecular forces, we know that the ion dipole is the strongest. The hydrogen bond is the second strongest. The dipole-dipole is the next. And then we have what we call induced dipole. So induced dipole basically means that, or ion-induced dipole. It's like you have something that isn't too much form, it doesn't form a really strong dipole, but you put something positive next to it and it gives it a little bit of like a wave. So it kind of induces it to form a dipole. And I'll show you examples of this in a second. Yeah. Now those guys are a little bit weak. They're 3 to 15, right? So they're weaker than the dipole-dipole. And then finally, we got the dipole-induced dipole. So basically where you have a dipole that's forming and it induces something else to form a dipole. I know you guys are like, what the hell are you talking about? It's just all these dipole, right? And then the last one is an induced dipole. So that basically happens when we have something that is considered to be relatively like non-polar. And so if it's non-polar, you guys remember polar, non-polar? You're alive. Okay, so the last one is just like I said, and those are often called London or dispersion forces, London forces or dispersion forces. Now, again, they're like when you have things that are non-polar, okay, non-polar molecules, okay? So let me kind of explain this to you with the picture, because the picture speaks better than me just saying dipole, dipole, ion dipole, dipole, dipole. Okay, so clear. Okay, so here we have two dipole-dipoles that are forming, right? Okay, again, partially positive, partially negative. Okay, so as we put these dipoles now next to each other, they're going to induce each other, right? They're going to have an effect on each other. Okay, so this positive is going to induce this negative, right? Okay, so in terms of dispersion forces, what happens is that you have those things that are slightly different. Like if you look at carbon and hydrogen, they're slightly different from each other in terms of the electronegativity. Very little. It doesn't make too much of a difference in the big picture. But if you look at it, carbon has a little bit more electronegativity than hydrogen. Very little, but it does. And if we sit there and play with that, they're going to form what we call dispersion forces. It's going to be weak and it's going to happen. Occasionally going to pull a little bit over there, and then it's going to shoot back. And it's going to pull a little bit over there, and it's going to shoot back. But that's going to induce the next molecule to do exactly the same thing, right? So as this guy becomes positive here on this side, let's say this side, my hand, this side is positive, this side is negative, right? So if I had another meat right here, it's going to be the guy that's next, right? Because that positive that was here is going to pull over that negative. It's going to touch that negative. And then it's going to be the next piece. And then the next, like a domino effect, exactly, just like a domino effect. And so that's dispersion, right? But it's going to be so quick that it's going to be really weak and it's not going to be strong. It's going to be really, really loose. Now, if you have a whole bunch of them, that adds up, right? Okay, so if we had a big molecule, a really long molecule that kept doing that, right? Well, it's going to kind of compensate. So the longer your molecule is, the more dispersionary forces you have, or dispersion forces you have, and it's going to increase that overall energy that it's going to take to break it. Okay, so if we're talking about, let's say, carbon chains, right? So if we had a carbon chain, let's say we have methane, CH3, methane, sorry, CH4. Methane has only one carbon. But if we have octane, octane is it gasoline, right? Octane. So that's C8. Now we have to remember this. 6 times 2, 12, plus 6. Okay, so H, 18. Okay, now we know that octane is a long carbon chain, right? Can you tell me something? And we know that methane is only one carbon. At room temperature, what state is methane in? It's gas, because think about farts, right? Yeah, right? Farts, right? So we know it's a gas, it's gaseous, right? You know, you toot and it's not liquid. It's, you know, if it's liquid, then there's something else going on there, right? So, okay, so we know that, right? Okay, now, but think about gasoline. Gasoline. Now, I go to the gas tank. If I just start spraying it on the ground, what happens? Do you see vapors or do you see it falling on the ground? Or do you get it all over your hands? Have you ever put gasoline and pulled it out and or all over your pants? Let me tell you, I have. These are the pants I got them on. So what was that? Yeah. What was that? The jug, right? Is it a liquid or is it gas? It's a liquid. Why do you think it's a liquid? What was that? Okay, so we know gasoline is a liquid, but methane is a gas, right? Methane, think about it, right? Just think about it for a minute. Methane has one carbon. If we have one carbon of methane interacting with one methane interacting with one methane, is there a lot of intermolecular forces going on there? No, you just have that one carbon that's going to be causing things to happen, right? So that carbon is going to get that slight negative, that hydrogen is going to get a slight positive, and it's going to induce, but it's going to be really weak. You don't have a long chain, right? Where octane, you have 8 carbons that are all connected together. And so because there's so many of them, you have a lot more intermolecular forces, and it causes it to be a liquid, right? So I'm going to ask you this. Let's say we had C22H 40, 46. Okay, we have this really long carbon chain, right? And we have gasoline. Which one would you expect? The gasoline. Why? Because it's shorter. There's not as many carbons for it to sit there and interact with, right? That's long chains of carbon. So let's look at it. I'll show you what we're doing. Can you see the class? Can you see the class, Marisol?
Yeah.
Okay. Good. Oh. We're gonna get together, right? Okay. So you guys are doing okay. Now. Okay. Okay. Now we're going to pretend to be like 5 other people, right? So going to be quieter. Okay, so we're on it together. We're on it together. Okay. Okay. So now the thing is that I'm going to still interact with him. He's going to still interact with 1, 4, 1, 4. Still interact with her. She's going to, and then if we move down a little bit, we're still going to be interacting, right? it's going to take a lot more energy because we have this interaction going on between two molecules, right? As well as you guys forming the intramolecular interaction, okay? Where the electrons are being transferred all the way around. But that's going to induce us to interact with each other. So it's going to take a lot more. So the longer you are, the more interactions you're going to have. Okay? There you go. I know. You don't want to be in okay. So those chains, right? The more those chains get, the longer they get, the harder it is to break, right? It's going to take more energy to break. Okay. Now, let's sit there and let's think about this. If we start adding things like fluorine, chlorine into those molecules, right? We have those chains and they have chlorine, fluorines. So that's going to add even more strength because those guys are electronegative, right? That means they're really attracted. They're like, oh yeah, you know? So it's going to take even more energy, okay? Does that make sense? Okay. Okay, so if we take a look at this. So we have fluorine, we have chlorine, we have bromine, we have iodine, and we have acetylene. As the molar mass gets bigger, our melting temperature gets bigger, right? So like for instance, fluorine, it's basically a gas at room temperature. So its melting temperature is 53 degrees Kelvin, right? 53 Kelvin. Okay. Its boiling temperature is 85 Kelvin. Now, this kind of makes sense to us too, because it's tiny, right? Remember fluorine? Tiny guy with a big attitude, right? Oh, he is like, you know, but he's tiny, right? Okay. Now, chlorine is kind of like fluorine's bigger brother, but, you know, not smarter or not stronger, but bigger brother, you know, because he's bigger in size. Okay. And so it's going to take a little bit more because he's a little bit bigger, you know? And then bromine is bigger than chlorine, so it's going to take a little bit more, right? So as we get to bromine and iodine, for instance, iodine is a solid at room temperature. 270 degrees Kelvin is 273 is what? Kelvin. 273 Kelvin is what? If it's 200, it's 0, right? 0 degrees Celsius, right? So what is 387? You guys didn't bring my calculator. 14, right? That's right. Is it? Did you say 14? Okay, so 387 is what? 114, right? Okay. So at 114 degrees Kelvin, 114 degrees Celsius, it starts to melt, right? So that means it must be what at room temperature? A solid, right? So at room temperature, it's a solid, okay? Where we know that bromine is a gas at room temperature, right? Based upon temperatures that we have, right? So as those molecules get bigger, it's going to start affecting that, okay? So the bigger you are, you're probably going to end up being a solid, right? So as we go down the periodic tables, we get to that solid state, where the stuff before it are gases, right? Because if you guys remember, where's nitrogen at on the periodic table? Which period? period? It's on the 15 period? Second period. Okay. Yeah, okay, second period. Where is phosphorus at? Y'all are rusty, huh? Where did you say? Third period, right? So, but we know that phosphorus is a solid, right? There's a couple things that we know about phosphorus. When phosphorus is formed, what is it? What is it a polyatomic, monoatomic, diatomic? Poly, right? So it's P4, right? So it's big. And we know that the majority of it is going to be a solid. It's not going to be a gas. So as we go down further, right? So if we had, let's see, what is after that? We have arsenic would be underneath phosphorus. So what we expect arsenic to be? Solid, liquid, or gas? Solid. Mercury is a hot mess. Yeah, okay. It's a liquid. It's a liquid at room temperature. It is a hot mess. Okay. So if we go down that row, we'd expect as you get bigger, you're going to take more energy to, and think about it. It makes sense, right? If you're big, doesn't it take more energy to get you to move, right? So let's say we had somebody who's really, really petite, right? And let's say you were playing football, right? And you were, okay, so who are you going to go up against? A little petite person or the person that's like really, really big, right? You're like, who do you think you're going to move, right? Most likely the little petite person. Everybody's going to go up and go, okay, I'm watching that person right there, you know? I'm not getting that one, you know? So, okay, makes sense? And if you kind of think about it like that, it'll help you with the process. Okay, so this is just basically showing exactly what I just told you, right? So here, these molecules these are all, oh, you guys will love this in OChem. So this is, this here is called neo pentane. This is isopentane, and this is N-pentane. N-pentane is a straight line of just carbons, 5 carbons that are attached. Isopentane is, well, as you can see, it's a little bit of a mess, right? So you have 1, 2, 3, 4, and then the 5th carbon is kind of in back. Okay, what's that? Yeah, it is high. Okay, and this is the structure. This is what it looks like. Okay, and then this here is your neopentane. Okay, so if you look at the boiling points of each of those, neopentane is 9.5. Isopentane is 27. And N-pentane is 36. So the boiling point of the neopentane is less than that of the N-pentane. Why? So I'm sure, because you have more surface area, right? This here gives us more surface area than this guy. And then this gives us more surface area than this guy. So the more surface area you have, right? Kind of like we were talking about. Oh, you can rub up against each other for a while before you're let loose, right? Okay. So the bigger you are in terms of surface area, you can get the same chemical compound, I mean, in terms of chemical formula, but if you take up more surface area, your melting temperature is going to be different than that. Okay, because these are all exactly the same chemical formula. Okay, makes sense? Okay, so let's see if you guys get this and got an understanding of this. Okay, order the following compounds of a group 14 element and hydrogen from the lowest to the highest boiling point. We have CH4, we have CI4, we have GE4, and we have CN4, I mean H4. Sorry. So Which one is going to give us the lowest boiling point, and which is going to give us the highest boiling point? Explain your answer. Yeah. Okay, we've got some answers. What do you guys think? Already in order. So which one is going to have the lowest boiling point? Yeah. Yeah, because as we go down, it gets bigger. Okay. Okay, so in real life, how does this work, right? So, okay, we take a look at the gecko, right? The gecko's feet. The gecko has setas. And then these guys, they actually form what are called spatulas. And so all of these little hair-like fibers, right? The more that we have, the better we stick, right? So the gecko sticks so well because it has tons and tons of these little fibers that are interacting with the surface, right? And these interactions, they're not strong interactions. They're just a whole bunch of little weak interactions that are all building up. Okay. Yeah, kind of like Velcro. Exactly like Velcro. Yes. Okay. So this is an example of dipole-dipole interaction. So that positive interaction with that negative. Okay. And then we could get it interacting in this way as well too, where this negative is interacting with that positive. So we could have end over end or it align straight up. Both of those are going to affect, right? So in the case of hydrogen bonding, there's a water molecule, there's another water molecule. This is going to form what we call that hydrogen bond with the other. That interaction, that partially, this guy's partially positive, this guy is partially negative, right? And they're going to be attracted to each other because there's partial charges. Does that make sense? Okay. So that's why water behaves the way it does. Right? Excuse me? You got to say it. S is sulfur. We're talking about. Oh, that's not S, it's delta. That's a delta. Yeah, sorry. Yeah, delta. So that basically means partial. Like, you know how like a complete charge, something that is total, right? Partial is like a fraction of it. Okay. Sorry, my delta looks like an X. It's a Greek delta. It's a lowercase delta. Okay, so let's see. Okay, and so things that are going to form hydrogen bonds. So when you have a hydrogen that's covalently bonded to an oxygen or a fluorine or a nitrogen, those are going to be able to form hydrogen bonds with each other, those molecules. Okay, and those are going to be stronger, right? They're going to be stronger than dispersionary forces. They're going to be stronger than dipole-dipole, right? Okay, so here we have, this is, so this is H2O, this would be H2S, this is H2S2, this is H2TE, okay? And then these are the hydrogen with chlorine and then bromine and so on and so forth. Now, it's important, right? You guys take a look at it. This is what you would expect to be the case, right? Because we know that oxygen is smaller than sulfur, right? And then oxygen is definitely smaller than selenium, right? But in reality, this is what happens. Why? Because it forms a hydrogen bond, right? Because oxygen is electronegative, right? And it has that stronger pull, and it causes that difference between the hydrogen and the oxygen to be so different, so strong, compared to something like sulfur or selenium, right? So the intra is affecting the inter. Again, remember intra, meaning enter, like inside that molecule, right? And inter means across, right? Interstate, right? Cross states, okay? Okay, so in that case, because of the hydrogen bonds, it's forming true hydrogen bonds, rather than in this case, where it's forming dipole interactions. Yes, that's the thing about a lot of molecules will have combinations of dispersionary forces, dipole, hydrogen bonds, so you could have, depending on the molecule that you have, you could have it all, right? Okay, makes sense? That's right. So if you have something that has a very strong electronegativity, like fluorine, oxygen, and nitrogen, particularly those, right? Those guys are probably going to be forming hydrogen bonds, especially if it's attached to a hydrogen. They're going to be forming hydrogen bonds. So you want to take that into consideration as well. Make sense? Okay. So DNA, right? You guys know about DNA. You know that it's very stable and it's formed this beautiful helix, and that helix stays together and it's really hard to break it apart, right? It has special machinery that is required to help it break apart because it's pretty strong, right? Now, why is it so strong? Those two strands, why are they so strong? Why does it require special machinery to sit there and get them to split up and unwind so that we can express those genes? Hydrogen what? Hydrogen bonds, exactly. You have a whole bunch of hydrogen bonds, right? So if you sit there and you look at this here represents, so this is actually the DNA molecule, right? And what happens is that on one strand, it forms a hydrogen bond with the other strand. So this here represents one strand. This represents the other strand. You have a hydrogen bond here, hydrogen bond here, hydrogen bond here, hydrogen bond here, hydrogen bond here. So we know that when we do get that those base pairs, how many of you guys take bio? Okay, half of you guys took bio, the other half hasn't. Okay, so let me tell you about this real quick. Okay, so DNA is composed of 4 bases. We have A, T, so A stands for adenine, T stands for thymine, G stands for guanine, and C stands for cytosine, okay? Now, A and T, they pair up, they form a hydrogen bond together, and they match up, right? So they're considered base pairs, right? Okay, and then, oops, do that. GC pair up, okay? Now, AT, this is the adenine, this is the thymine. It forms 2 hydrogen bonds between the side bases. Now, those 2 hydrogen bonds are pretty strong themselves because they're interacting. They're just forming that nice hydrogen bond. Now, a piece of DNA, let's say for a gene, right? A gene is going to be like 6,000 base pairs. So you have a whole bunch of hydrogen bonds that are formed between that 6,000 base pairs. Now, on the average, it's estimated that our genome, which is a little more complicated than other genomes, it's about 55% of it will be GC. GC has 3 hydrogen bonds. And then that means 45% of it is AT, right? So you have a shitload of hydrogen bonds, right? So it takes a lot of energy to sit there and separate them. So that's the reason why it takes these special enzymes to sit there and open it up. Otherwise, we'd sit there and start expressing genes at the drop of a hat, right? If we didn't have the hydrogen bonds. Exactly, yes. So, but those are, so CRISPR was actually a result of well, it was thought to reside from a virus initially, right? And so, but it was in simple organisms like bacteria and stuff like that. Okay. And so, yes, that's the reason why CRISPR has to be used to sit there and change that genome sequence. Part of the reason. There's other things, but part of it. Okay, so properties of liquids. I know, long list. I hate them. Okay, so we know that the physical properties of liquids can always be explained by these intermolecular forces. Okay, so we kind of talked about water. We understand a little bit why water it takes so much energy to boil water is because of those hydrogen bonds. Cohesive forces are going to be the intermolecular forces between identical molecules. So cohesive, right? So that just basically means they're identical. Right? So think about twins. Adhesive forces are going to be interactions between different molecules. So adhesive, tape, tape on the substance, that's an adhesive, right? Okay. Surface tension is just forces of attraction between liquids by the intermolecular forces, okay? That is created by the force of the surface. Okay, so surface tension, like you guys think about a graduated cylinder, right? It forms that meniscus. So that it going up like that, that's a result of surface tension. Okay, so are those adhesive forces or are those cohesive forces? So let's talk about, we're talking about the meniscus forming on a graduated cylinder. So here's my graduated cylinder, and that's my water. Okay. So is that cohesive forces or is that adhesive forces? Okay, so what is the definition of cohesive? Identical molecules. So is glass and water identical? Okay. Yes. Yes. Mercury is a hot mess. Yeah. I told you. I was kind of confused on that. Okay, so that talks to us about which force is greater, cohesive or adhesive. So if it's going the opposite way, if it's going like this, that's right. Cohesive forces will be stronger in that case. So if it's upside down, this is Mercury, this is our Mercury, right? That means that the cohesive forces, so the interaction between the mercury molecules, are stronger than that of the mercury in the glass. Mm-hmm. That's right. Okay. Okay, so capillary action is going to basically involve differences between intermolecular forces between the liquid and the liquid and the surface of the glass. Okay. So in that case, adhesive forces are going to be greater than the cohesive forces. Okay. So if the adhesive forces are greater than the cohesive forces, that means it's going to pull itself up on the thing. So you get capillary action happening. Okay. Now, if it was the other way around, then that's how we end up with that surface tension, and that's in the case of mercury, right? Okay, so viscosity is basically the resistance to flow due to intermolecular forces. So you have gasoline, which consists of a long carbon chains. They're 3 to 8. So we know that gasoline, octane, 8 carbons, right? It's going to have a low viscosity compared to that of oil, which has 20 or more carbon chains, right? So if we pour gasoline and we pour oil, which one is going to pour faster? Gasoline. Okay. Okay, so this looks at the viscosity. So this is the viscosity of water. This is the viscosity of mercury. This is the viscosity of ethanol. This is the viscosity of octane. This is the viscosity of ethylene glycol. This is the viscosity of honey. This is the viscosity of motor oil. Okay, so we know that water has hydrogen bonds, right? And so that's pretty much all it has is hydrogen bonds. That's its viscosity. We know that mercury, this is the viscosity of mercury. Mercury has its own, again, hot mess of the self. Here, ethanol. Ethanol is going to have a combination of those dispersionary forces as well as hydrogen bonds. Right? And then octane is only going to have dispersionary forces. Right? So it's weaker, right? That's right. Its viscosity is less, right? And then ethylene glycol, which we have this hydroxyl group and this hydroxyl group. So you have 2 sets of hydrogen bonds that are forming, as well as dispersionary forces. Okay, and so its viscosity is greater. And then honey, big old long chains of sugar, sometimes it's sugar, sometimes it's starch, it's all over the place. So you're going to have OHs going everywhere and dispersionary forces, it's going to be a little bit of everything. Okay, makes sense? Now I want a honey and biscuit now. I know. I know by the time we get out of here, it's going to be closed. Oh, it is so much better. Their biscuit is so much better. Okay, so we've already talked about cohesive versus adhesive, right? So we know the difference between cohesive. Cohesive means they're identical, and adhesive means they're different. Okay, so here this guy is called a water spread. It actually just glides on the surface of water, right? So what was that? Okay. And then we talked about capillary action earlier, right? So in that case, oh, and this is a good example. We have mercury in one case and we have water in the other case, right? So mercury, as you said, versus water, which is the other direction, right? I know, I need a bigger picture. Okay, so here we have dew on a spider web. Okay. Yep. Mhm. Yeah, you're using both, but it just means that you have one is going to be greater than the other, right? And so both of them exist. It's not like you have one or the other. In most cases, you have both, because if you think about it, even with water, right? You have the meniscus, but you still have water interacting. So you have both both the cohesive, or the water interaction, as well as the adhesive. You know? It's just a matter of who's stronger. In the case of the water strider, the cohesive. Yes. So it's so you're right. It isn't sticking to the water. So its hand isn't sticking to the water, right? So and so it's gliding on the water, right? So you're right, because they're two different. This guy is going to be weaker than the other. Where this guy is going to be stronger, the water itself is going to be relatively stronger compared to that. So unlike us, where we just kind of fall right through, right? And then get the water all on us, right? So okay. So this is your example of the wine whipped up with the paper towel. Okay. Okay, so here, this is an example of the capillary action, right? So here we have water, and then the water is rising up the tube, right? Where in the case of mercury, it's capillary repulsion, right? Because we know that the mercury itself is going to have a stronger cohesive or adhesive. Cohesive. And this can all be calculated. That height, okay, where ST represents the surface tension. This is the cosine of the angle, and then radius of the tube, the density of the substance we're working with, and the gravitational pull, which is 9.8 per second. And if you guys remember, think back, we kind of talked about this when we were talking about barometers. That's right. Remember the little U things that we use for measuring gas, the height and the density of it. Yeah, so. Okay, so let's go ahead and see if we can get our example here. So at 25 degrees Celsius, how high will the water rise in a glass capillary tube with an inner diameter of 0.25 millimeters? For water, the surface tension is 71.99 nanometers per meter. And then the density of water is 1.0 grams per cubic centimeters. 1 meter equals 1 kilogram per meters second squared. Okay, how are you guys doing there? What's that?
What?
Confused? Okay, so let's go with a couple things. We can start off with our density. We know the density is 1 gram per cubic centimeters. So if we change that to kilograms per cubic meter, then we could just use everything else, and we also change our millimeters into meters, right? So let's start with that. So we know our equation is going to be this 2 plus t, and cosine of, in this case, 0 will be 1. Is that right? Okay, so it's a 0 degree. And then we have R, G, and rho, right? Okay. So change our radius into meters. But that's inner diameter, right? So we know that that's going to have to be divided by 2. So we're looking for R is equal to millimeters, divide that by 2. And then we need to change that from millimeters to meters. How do I change that to meters? Okay, so we have 1,000 millimeters equal 1 meter. Okay. So we have what, 2.5, oops, sorry, 1.25 times 10 to the minus 4, I believe. Is that correct? And then we have to change our density into per cubic centimeter. My handwriting is horrible. I know you guys have missed it. Okay, so if we do that, let's just do it like this. So if I want to go from cubic centimeters to meters, so then I know that 100 cubed centimeters is going to equal 1 meter cubed. Okay. I also know that that 1,000 ring. 1,000 grams equals 1 kilogram. Check for 3 grams. Okay, so then grams are going to cancel out. Centimeters are going to cancel out. And then I'm going to be left with 1.0 times 10 to the third. All right. And that's kg meters cubed. Then I just plug it all in, right? So, oh, we have to change this into millimeters, so we know that's 7.1 times 0.99 times 10 to the minus 2. That would be Newton meters. We have to multiply that by 2. Divide that by our radius, which is 1.25 times 10 to the minus 4 meters. And then we multiply that by down here. 1.0 times 10 to the minus 3. Oops, not minus 3 to the 3. My bad. Okay, and that's kg. Cubed. And then our density, which is 9.8. Okay. Acceleration, which was per second squared. Okay. What do you guys get? You had a look. It's millinewtons. The unit was in millinewtons. So I needed to change that to newtons. Piece cake? Okay. You guys plug it in? What you guys get? 27 feet? Okay. Piece cake? No? Did you guys get the same answer? I was trying to figure out what you guys are looking at. I'm like, it's right here. What are you looking over there for? And then I realized it's the same thing over there. Okay. So we're going to stop here with our calculations, and then we'll finish up with transitional phases when we get back on Thursday. Okay, so we'll take a 10-minute break, and then we'll start the lab.